before we go into the Ramsey-Coutts-Koopmans model and solve it with the relaxation algorithm, I thought I'm going to provide you with a small visualization of the Newton-Raphson method. Remember, we might end up with a highly nonlinear system, maybe also high dimensional, and we want to solve it. And this is often quite challenging, to say the least. But one thing we're really good at is solving linear systems, even in high dimensions. So the idea is that maybe if we have a nonlinear system and we want to solve it, maybe we can approximate it with a linear system. So, and the idea here is that we have to linearize the system somehow. Okay, and what do we need for a line? In the univariate case, it's easy. We need some point where the line goes through, and we need a slope. And the slope is typically obtained by taking the first derivative, because this provides you with the slope in this given point, right? So you need differentiable functions. Your system needs to be at least locally differentiable. So once you have your point, and the point, how do you get the point? Well, ideally you have an educated guess, but you could also just, guess somehow. The closer you are to the truth, the better. Okay, so in this case, in this visualization here, our initial guess is 0.7. And you see the linearization around, and we have this nonlinear function, the blue one, right? This is the solution we're after. The solution is here. The true solution is 1.4. So we want to find this. And if we linearize the system around our initial guess, it works quite well in some neighborhood, right? But the further we go away, the worse it gets. So maybe using a linearized version does not really cut it. But the idea of the Newton-Raphson method is now that, if we end up with a solution of the linearized system, what if we just take this solution and evaluate our system and our slope at this new solution? In the ideal case, if we are already in the slope, in the solution rather, then nothing would change. But if we just take our approximated solution and plug it in as the new initial guess and linearize around this new initial guess, you visually see already that the new solution suggested in the second round is much closer to the true solution. And if we do this a couple of times, now we plug it in again, linearize the system around this new solution, we are already quite good. And now the question is, how precise do you want to be? Well, because the more often you do it, the closer you get. And here you are already in the really small territory. If you do it once more, I guess, yeah, we're probably close to machine error, in almost every application this is good enough. And you see, maybe linearizing the system in the first run didn't really provide us with a good solution, but iteratively linearizing helps us find the true solution. And this is of course, a toy example, right? It gets a bit difficult to visualize in high dimensions, but I hope you now have a good intuition on how this works.